Welcome to BazAI. Today we're breaking down one of the most important concepts in large-scale system design, database sharding. At the simplest level, sharding is about survival. When a single monolithic database can no longer handle growing data size, read traffic, or write throughput, vertical scaling stops working. You can't keep adding CPU or memory forever. Sharding solves this by splitting data horizontally across multiple independent databases called shards. Each shard holds only a subset of the total data, but together they represent the complete system. Once data is distributed, reads and writes happen in parallel, throughput scales almost linearly, and failures are isolated instead of taking down the entire system. There are multiple ways to shard data, and each comes with trade-offs. Range-based sharding splits data by value ranges, such as price, user ID ranges, or timestamps. This is simple and efficient for range queries, but it has a major weakness. If traffic concentrates on a specific range, you end up with hot shards, uneven load, and degraded performance. Key-based sharding, also known as hash-based sharding, uses a hash function on the shard key to determine where data lives. This gives excellent load distribution and avoids hotspots. However, it breaks natural ordering, which makes range queries slower and more complex. Directory-based sharding uses a lookup service that maps attributes like region or tenant to specific shards. This approach is highly flexible and allows dynamic rebalancing, but it introduces an additional dependency. If the directory becomes slow or unavailable, the entire system is affected. In practice, large-scale systems often combine multiple sharding strategies to balance performance, flexibility, and operational complexity. The most critical decision in any sharded system is choosing the shard key. A good shard key must have high cardinality, so data spreads evenly. It should have uniform access frequency to avoid hotspots. And it should not be monotonically increasing. Keys like timestamps or auto-increment IDs may seem convenient, but they silently create unbalanced shards and bottlenecks over time. Once data is sharded, every request must be routed correctly. This can be done in three ways. Shard-aware clients route requests directly, but are tightly coupled to shard topology. A dedicated routing tier centralizes shard logic and offers clean abstraction at scale. Shard-aware nodes sit in between, providing a balance of flexibility and control. Most modern architectures prefer a routing tier for long-term evolvability. Finally, sharding is almost always combined with replication. Each shard has a leader that handles writes and multiple followers that serve reads. Leaders are distributed across nodes, so no single machine becomes a bottleneck. This design delivers high availability, fault tolerance, and horizontal scalability, but it also introduces coordination and consistency challenges. Sharding is not just a database optimization. It's a foundational architectural decision that impacts APIs, query design, consistency models, and operational complexity. Master it, and you're no longer just building applications, you're designing distributed systems.